So first of all, I need to say that our code is in Jupyter Notebooks and PyTorch. So if any one of you want to see the code, just use Will's exploits and we'll be good. Okay, so this is Quiver. I think we did, Gal and I, and let's begin. Those three logos are logos for three fairly new tools, although they're pretty famous. The first one is DALL-E 2, the second one is GPT-3, and the third one is GitHub's Copilot. And let's start with some examples. So DALL-E 2 can create an image from text. In that example, we can see a cybersecurity researcher sitting on a beanbag in front of a pool in the desert in a fancy hotel trying to reverse engineer a nation-state malware working on a presentation in a realistic style. So that's you guys. If you can't connect with that one, maybe this is you guys. As you can see, it's not very good with text, but you are all cybersecurity researchers. GPT-3, well, GPT-3 is a model that can generate text. Its applications in cybersecurity, you don't really need to read that. What you need to know is that, except for I've written only the gray part, and GPT-3 created the rest. In the same manner, GitHub's Copilot, this is code that I actually use, just some authentication stuff. And when I've written that, I was just starting to use GitHub's Copilot. And only the gray parts are the parts that I've actually typed in, and GitHub's Copilot did the rest for me. You can see that even you have the function that I made a typo. I called it anonymize password, and it understood that I mean to anonymize the password. Okay, so what's common to all those models? All those models understand language. They share common language features between users or between applications, and part of the learning process is unsupervised, a term that we'll speak about later. The question is, can we do the same for the language of command lines? And the answer is yes, but well, no. Currently you're thinking what am I doing here? I came to a cybersecurity conference and we're here to talk about deep learning. Gal and I are not, firstly, cybersecurity people. We are coming from the field of machine learning and deep learning, and we tried to get a free trip to Phoenix, so we managed to. We're going to talk about the problems we had with command lines before, then what changed that made this one possible, then about our package Quiver, which, as you've seen, the acronym came first, and eventually we'll show the big show of what we've got. This is Gal.
Yeah. So I'm Gal, staff data scientist in SentinelOne for the last 6 years, a father of 2, and Breaking Bad is the best show ever.
And we're mostly the same person. I'm Dean. I'm a staff data scientist in SentinelOne for 3 years. Actually, Gal got me into the company. I'm a father of 1, and Breaking Bad is the best show ever, except maybe The Wire. So because we're not in a deep learning conference, let's do a few-minute intro to machine learning and deep learning. What you see here are cats and dogs, and those are called samples. We want to create an algorithm that can distinguish between cats and dogs. One way they tried to do this before is with algorithms that people are trying to generate. Maybe if it has the ears are that way and the tail is that way, maybe it's a cat, maybe it's a dog. And it was a very hard problem. Even a person couldn't tell you why am I seeing a cat or a dog in this picture. I just when you know, you know. So we tried to make this in deep learning. We just show the computer, the algorithm, many examples of cats and dogs. This is called tagging or labeling. And you can go into Google and just type give me pictures of dogs. Those would be the green ones. And then give me pictures of cats. Those will be the red ones. And then you show the algorithm enough samples, and it will create an algorithm using what we call training. Then when you give it a new sample, the gray one, you don't tell the algorithm which one it is, and you put it in the algorithm, and the algorithm spits out, well, this is a cat. In the same fashion, it says, this is a dog. Now, that was a pretty easy problem because you could search that on Google, give me cats, give me dogs. Enough people tagged cats and dogs in the history of time. But as my friend John Nisbet, he's not actually my friend, but he's a very famous person, he told, we are drowning in information, but we are starved for knowledge. Like all of us have a lot of stuff, like pictures of things, command lines, language, many things. So what we have many command lines in SentinelOne. The thing we don't have is tag data or label data. The people that can actually do tagging for label data, like saying, is this command line bad or good or bad? The green ones are good, the red ones are bad. Most of the people that can actually label the data for us are here in this room. So I could ask you guys, instead of listening to the talk, give me 10 minutes of your time and start tagging data for me. But that is a very manual process, and that would not scale up. So what changed? Well, in the old time, meet Mimi. Mimi Katz, she's Jewish like us, and she has a task. Separate, like she gets many papers, and we tell her, separate those papers between like stuff about cybersecurity and stuff about machine learning. Even if she doesn't know like the two concepts, maybe she can try to distinguish between the two. The problem is that the papers are in Hebrew, and she doesn't know Hebrew. So she could maybe try and do so if you give her like thousands of examples. Maybe she can try and understand the hieroglyphs of Hebrew and try to understand which hieroglyphs are machine learning and which hieroglyphs are cybersecurity, but that would, again, not scale up. So instead, we can introduce a baby. This is a Wanak or Wanak cry. Wanak also doesn't speak Hebrew. He doesn't speak any language. He's a baby. But what he does have is time, because he's a baby. And people are speaking Hebrew and English next to him all the time. Where does it meet us? Well, this is the old way we used to do things. Like the first one is task one. Give the student a task to distinguish between two things. Then give another student a task to distinguish between two other things. A baby can do something else. We can try and give it books. Like first, understand language, understand what's Hebrew, understand the relationships between words, just understand the language. Then when you give them tasks, we can give them a lot less data to learn on the tasks instead of like giving it like the whole history of data for each different task. And you're probably starting to understand where we're going with this. This is, again, Quiver, and what Quiver understands it can do is that Quiver is the baby. We have, again, in SentinelOne, we don't have a lot of labeled data about command lines, but we have a lot of command lines. So we can just ask Quiver, we'll start reading those command lines and start to understand the language of command lines. Of course, this is not as very simple. We have many command line languages and stuff like that. But basically, you can just tell it to like start reading command lines. The way we do this is by a thing we call the masked language model. And basically, we give it like a sentence, and then we hide one of the words or a few of the words, and then we can try it like tell it, based on that sentence with the hidden word, try to predict that word. That's the way the model learns. This is how we create, like, we virtually create label data for the task of learning the language. Now when we learn the language, we can deploy it into different tests, such as like classify between different executables. We can do anomaly detection. We can, of course, try to do distinguish between malicious and benign command lines, and so on and so forth. That's, of course, like we have a saying in the data community that given infinite time and infinite data, the model will learn everything. But unfortunately, we don't have infinite time or data, so we try to help our models. In our specific case, we try to take the command line wisdom and deploy some regex rules on it. So you can see that we are trying to mask different directory paths. We try, we can understand when we're seeing a local IP or a public IP. We can see when we have base 64 strings, and all those kinds of rules that we've created to help our model.
So given that we have this data set of command lines that we pre-processed and we want to feed it to the model, now eventually, as we mentioned before, the model receives numbers. It needs somehow to translate this string into vector of numbers that it can process. So the building blocks of language, which is in our domain called tokens, let's see how we can extract them. So there are several approaches. The main one will be to dissect these strings into words by using several separators like slashes or white spaces, which is great if you want to keep the high-level entities. For example, argument names. You see that the argument name is still intact, but it makes our lives a little bit difficult when we tackle new strings. For example, if we see a new command line with a new argument name, we need to handle it somehow because we don't see it in our vocabulary. So a different approach will be just to split the whole command line into single characters and single chunks, which is the minimum amount, which from one, so it mitigates the issue of unknown data that we tackle, but it makes it more difficult to understand the higher level entities, and it will take the model a lot more time to learn. So there's the middle ground, some cool concept that was popped up several years ago, which called subwords. I won't get too much into details how it's happening, but it allows us to dissect the text into generic blocks. You can see that these hashtags, double hashtags in some of the tokens, which mean it's an end of a word or a start of a word, and it's give us the good parts of both words. So what good output, the awesome thing we can extract with these models is feeding them text, for example, like a single token or a whole command line, and we can extract some vector of numbers that we can use for different tasks. And actually, as Dean mentioned before, we're taking these command lines, feed it to a model, which learn the, in general way, semantics about the command lines, and then fine-tune it to specific tasks. And during this learning phase, it's optimizing some, it's called weights, some numbers inside of this model, which will be different for each kind of the tasks. So we can extract command lines representations based on specific tasks that we are interested in. Okay, this was an intro about the core concepts of this model and how it works. Let's see some examples of the output, of the results that we got. So here's a nice blob. We took millions of command lines and fed it to some model and let it just learn the semantics of command lines. Each one of these dots that you see here is a single token from the text that the model extracted. Now we can take a look inside of these tokens and see if it understands some semantics about the command lines. Each one of the dots is a vector, and this is a two-dimensionality reduction of the results. So, for example, here you can see minus no profile token, which is a known PowerShell argument. On the left side, you can see it's a zoom in to the specific space location of minus no profile inside of these tokens representations. And as you can see, on white, you can see the no profile token, and the green ones are the ones that was mathematically the closest one to it. And on the right, in the small table, is the five most closest tokens to the specific token. As you can see, the top three, which was the closest ones are different PowerShell arguments or syntax, which is awesome because it really understands something about tokens from PowerShell command lines. And the bottom two is not related straight to PowerShell, but it's different arguments. For example, the second from the bottom is a Java argument, which again symbolize that it learns something about arguments to executables, which it's nice. Second example regard that is a different token, which is double hashtag .vbs quotes, which means the end of a file path inside of an argument value. As you can see in a similar way, you can see that the top three ones are different VBS tokens, but the rest of them are exactly in the same patterns, but with different file extensions. So it's .js, .bat, conf, pl, jar, and so on. And it really understands that these patterns, these tokens, are related inside the same space and give it similar vector numbers, which eventually led us to the conclusion, okay, we have something, it's not totally random, and we can try and take this model and fine-tune it to some task that we want. So the most obvious thing that we can think about was trying to teach the model whether a specific command line is malicious or benign. What we did is, okay, so we have this baseline, a language model that learn the general semantics, but we want to fine-tune it to this specific task. So firstly, we need some labels. SentinelOne got an MDR service which called Vigilance, which basically going through different cases, different threats that's happening in our customers' computers and decide if a specific case is malicious or benign. And we use these cases to try and decide and extract some command lines that we know it will be malicious and vice versa. So here you can see PowerShell command line from a specific malicious threat that was happening. And the model actually signed it as malicious, which is cool, but these kind of models let you extract something even more fruitful. You can try and extract for each one of the tokens how much it supported to the decision if a command line was malicious or benign. So for example, you can see here the different parts that led the model to decide this classification. So for example, here you can see like the invoke web request inside of this PowerShell, and some parts of the URL cause it to think this command line is malicious. In a similar way, here are another two examples. The middle one is another PowerShell malicious command line that the model decided it was malicious, and you can see on the areas it's focusing, like for example the non-interactive token, or there's like it's a little bit faded, but there's the sleep function in the end of the PowerShell command line, which it learned from the data that we fed it. What is malicious and might cause it to be a malicious command line. The third example is a benign, entirely benign command line. It's just a winword .exe executable that gave in some file path, and the model thinks it's very, sorry, I didn't explain that the red parts are saying it's more malicious, and the green ones led it to think it's more benign. And you see that the fact that the winword is the name of the executable and some string parts in the file name cause it to think it's a benign command line. So what can we do with this model beside just predicting on a single command line? So firstly, we can just take this model, and even if it's not 100% accurate, and take it and just throw every command line from a customer environment through this model. So it might have its mistakes, but it can help us as hunters, for example, find our blind spots, reduce this all the areas that we might miss, because there's a bunch load of threats, a lot of information just going through our customers' environments, and we have to focus somehow. So this tool can help hunters to focus on the areas that they might missing. And from other aspect, this kind of explanations to understand what caused these command lines to be more malicious or more benign can help us understand our customers' information and make conclusions. And even, for example, we can try and let's write a Yara rule that specific fits for these kind of patterns that we see on malicious command lines, or, for example, command lines that the model usually think it's more malicious. So this was one example. The second one that we wanted to talk about was executable classification. What we did is take our millions of command lines and split them by arguments and executable. And we fine-tune the model to try and, given set of arguments, tell me which executable is it. So another piece of art on the right side. You can see each one of these dots is another reduction to 2 dimensions of an arguments, a set of arguments, and the color is the executable. And as you can see, this representation is excellent. It's very, very good. Most of the clusters are very uniform, which means it actually learns something about which arguments are relevant to which executable. And there are, even more interestingly, there are clusters that are not unified, which make us think what are these clusters and what are these interesting command lines that look like different executables. So here, just to have a little bit more practical examples, you can see some of the clusters, like main executable, like CMD or VBC, and actually a cool byproduct you can see on the top, like 3 browsers, different browsers that arose in different clusters, but was around the same area in this n-dimensional space. But you can try and extract some cool information from these clusters. For example, some intent. Here is, for example, a cluster that was based from mostly communication executables. Or here you can see a cluster that most of the arguments inside was like Java arguments and one CMD, and if you print this CMD command line, it was actually execution of Java, which it actually makes sense, but this tool can be used to try and tag and understand the intent of specific command line without even looking on it. You can try and use this model to try and see a new command line that fell inside of one of these clusters to try and predict, okay, this cmd.exe did something that we know is maybe executing Java. And the last example here, as you can see, this big giant cluster is full of different PDF readers. On the bottom, you can see 2 examples of CMD and MS Edge that also open PDF files, which again, we can understand that these cluster, these representations in this cluster, we can tag it with some nice intent and try and predict for a specific command line. So I'm sure that there is at least one person in this audience that think, do this stuff can solve this thing with regex, sit and try and write sophisticated patterns, but the awesome part of these models, just feed them a bunch load of data. You don't need to really fine-tune it specifically for the task that you want. As we mentioned, I think it was like the first day, there are more and more attack vectors for third parties executables, and this thing, if you keep feeding it more and more data, it will understand better the semantics of command line and easily can be fine-tuned to the task that we want. And if the results won't be good, we still have a saved spot in art school. And that's it. Thank you. Any questions? Do you mean like given these representations that were created, whether we found something that we can like publish to the community and use it?
Well, more like, say I don't have the entire database of SentinelOne data to work against, but I do want something to push against as a threat researcher. Is there any direction you would push me?
Yeah, so this is currently like only at the research phase, but the same way you can use DALL-E 2, although you're not an artist, probably we've never met. You're not an artist, you're not a poet, but you can use GPT-3 and you can use DALL-E 2. Once we have like a working model, it should understand even like new stuff that are in that domain. So even if you give it like a new command line, if we trained it well, if you give it a new command line, it could say like the things that we've taught it to say. In that way, if we prove it successful and actually good, then yeah, of course we can do it. And one of the things that like is fairly new in our world is that like DALL-E 2 is one specific implementation of a bigger academic paper that's called CLIP, and basically the thing that the most special thing that DALL-E 2 had is the data itself, but it gives you the data. Now, if you say, I have more data, I can start from that model. The model itself is open source. You can start from that model and train it on your own. It probably take you a lot of time. You need many GPUs, but like it's available to you. It's just a question of like time and money and not like a proprietary stuff and stuff like that. Yeah.
So it depends. It depends what you exactly want to achieve, because overfitting, it sounds like it's the worst nightmare for every data scientist, but it might be good for you if you specifically want to find abnormal activity in a specific customer. If you want the model to be fine-tuned to a specific customer and extract information. It depends on the applications, but yes, exactly. I think one of the reasons we thought about, for example, normalizing paths or local IPs or base 64, it was to ease the training, but also let's not fine-tune it to a specific IP or specific directory names. So the road is still long before you get to something very mature that we can like publish publicly, but yes, it's something that needs to be thought about, and beyond that, like PIIs, for example, let's not give some attacker option to my IP is something, and we complete it to some DNS server or whatever, or something that's important to the customer. But yeah, things to think about. Yeah.
We're not product people, so once we show it to like the PMs, if they like it, like as Gal shown, the part with the green and red parts is very cool to us. Will customers find it like useful? That's not on us, I think. I think it will be cool to show it, but again, the PMs will decide. Thank you, guys.